might have to wait here until the other task is out from the critical region. Okay, so what could we do? So we could, for example, think about using two flags here, flag 1 and flag 2 for each process. And then when we are about to try to enter the critical region, we set flag 1 to 1. And then when we leave the critical section, we set it to 0. And then in this try state, we check here if flag 2 is equal to 0, which is now set by the other task. So if it's not 0, it will go back here and you will try again. So, if you take a look at this, will this work or not?
No, there's a chance of wait.
There's a
chance of having a lock.
Yeah. Okay. So what is the lock situation?
Because these events are not instantly happening. They are taking some time, and if the process 1 and process 2 tries at the same time, both will block each other.
Yeah. So we assume that this updating this is an atomic operation.
Yeah.
So which state is a live lock state here?
Try.
Yeah. So if both goes into these two states, so P1 sets the flag to 1, so flag 1 to 1, and P2 sets flag 2 to 1, then we are here, right? And then both of them are waiting for the other flag to become 0, which will never happen, right? So they might be stuck here, so you have a live lock here. So this didn't work. Okay, so can we think about another way to do it? Yeah, so this was what I said. So we are in a busy wait loop here, typically live lock. Problem with animation. And this is a well-known protocol called Peterson's mutual exclusion protocol. So it starts in the same way. You set flag 1 to 1, but then it has another variable, turn, that is updated by both of the two tasks. And task 1 will set it to 1, and task 2 will set it to 2. And we can take a look at it. Okay, so you see, so task 2 starts in a similar way, so it sets flag 2 to 1. So now it indicates that, okay, I would like to enter the critical region. And then it's updating the turn variable again here. So let's say we're now in the situation where we start, T1 goes into this state, P2 goes into this state, and this is where we were in a live lock before. But now we see here both of them can proceed, but this one will set turn to 1 and this one will set it to 2, right? And assigning a variable is an atomic operation. Okay, so let's say now that we are entering these two states. So here, let's say we do this first. So when we are in this state and this state, turn will be 1, right? But when this one then has finished, turn would be equal to 2, right? So the turn variable will in this case be the last one to enter this state. So yeah, the identity of the task of the last one to enter. Yeah, and this will be used to sort out the situation. But we can just look at the easy situation first. So let's say P1 is starting, so we start here, and now we go into this state, so flag 1 is equal to 1, turn is equal to 1, and then we check if flag 2 is equal to 0, which it will be if you're still in the initial state here, right? And then you enter the critical region, and then when you're done, you return back to the initial state, and then the other task can proceed, right? But let's now assume that we are in the more complicated situation. Both of them have entered these states. And we assume that task P1 entered first and T2 entered second. So now turn will be 2, right? Will flag 2 be equal to 0? No, it will not, right? So this can't happen. So we will go into this state. And this one is here. So here we check if turn is equal to 2. That means that this task was the first one to update turn. Right? And then we, for fairness reason, we say, okay, now then I should enter the critical region because I was the first one to do that. If turn is equal to 1, then it means that, okay, P2 was the first one to enter the try 2 state. Okay, so then we go back and wait for a while. But if we were the first, we enter the critical region, and then we go back, set flag 1 to 0, and when flag 1 has become 0, then try 2 can enter the critical region. Will this work?
Yes, it will.
Yeah, it actually will. But this is not what you use in practice. You know why?
Too many states?
Yeah. But it's still not too many for 2 processes. But this will be very complicated if you have 3, 4, 5 different threads that you need to coordinate. And we needed to do this in multiple steps just to deal with the problem that we could not read and write to a variable as an atomic operation. So, since this is a very common problem that we need to solve in some way, there are other solutions. We will talk about what's actually used, and there is special hardware support for doing some things here. So this was just to summarize here. The turn variable is used to record which task was the first to change the value of turn. And this is correct under the assumption that you do atomic write. But it's complicated for more than 2 tasks. Yeah. So, inside a processor today, you have a special instruction and a special register called the test and set register. So the test and set register holds a Boolean variable. So, and it has a reset operation, change the value to 0, and the test and set operation, which returns the old value and changes the value to 1. So now, you see here, so, and this will be an atomic operation. So if there are two processes competing to execute test and set instruction on a register with value 0, one will get back 0, the other one will get back 1. So this can be used to synchronize which one was actually the first one to execute. So so it will only be the one. Yeah, one of them will continue, the one that got one back, and then it will be reset to 0 when it's done, and then the other one can do a test and set instruction again, and then continue. So we will not go into the more details on this, but it's just that this is supported in hardware, and this is used to implement what we will now talk about, namely semaphores. Any questions about this? So it's important here that you understand this problem, the race condition problem. That the order of execution, or in which order you execute the instructions, might affect the final result of the computation. And this should be avoided. So then you need to synchronize your threads. And exactly, so for the next project meeting, the first problem is a race condition problem that you need to solve. So there will be, it's an example I showed in last lecture. You have a couple of threads that are increasing and decreasing a counter, and you will see that you will get different results depending when you run it from time to time. So then you need to implement mutual exclusion to make this update of the shared variable and atomic operation.
Isn't combining the processes are also an option to get rid of this problem?
Yeah.
If I want process 1 to happen before process 2,
yeah,
then I can just put them on the same process and just call it process 1.
Oh yeah, of course. So so if you can sort of somehow compile them into one process, then you will have the same behavior every time. And there is a whole community for doing this. It's called synchronous programming languages. So basically, you build a static scheduler then, so it will behave in the same way every time. And that is used, for example, in aircrafts, but it's not typically used in the automotive industry, at least not yet.
It's more concrete,
but it's just a, sorry?
It's more concrete. You can be sure, like.
Yeah. But what you have to give up then is to have this flexible number of threads, for example. So everything has to be known when you at compile time. So in this case, when you have threads, you can start threads dynamically while you're executing, for example. So which also has some benefits. But depending on how safety critical the system is, you would like to do this or not. But people do this a lot, so this is what is mainly used. And synchronous programming languages is still a niche, I think it's fair to say. So we will come back to that, but Bengt probably told you about the rover that they sent to Mars. So even for the things they send to Mars, they implement with these kind of techniques. So it's used a lot. Okay. Actually, I think we will wait with this. So we will switch to semaphores directly. So a semaphore is a data structure that has a couple of operations. So technically, when you create a semaphore, you can think about the semaphore as an integer variable, but with a couple of differences. So like an integer variable, you need to initialize it to a certain value. But after that, you can only increment, so meaning increase by 1, or you can decrement the value by 1. But you cannot read the current value of the semaphore. And then you have this very peculiar behavior. So when a task decrements the semaphore, if the result is negative, the task blocks itself and cannot continue. So if you try to decrement a semaphore that has the value 0, then that task will block. Right? So it will switch from running to being blocked. And then it can continue later on when some other task has increased the value of the counter or of the semaphore. Then you can increment the semaphore, and if there are other tasks waiting, one of the waiting tasks will become unblocked. So meaning it will be changed state from blocked to ready to execute. And in FreeRTOS this is called, or to execute this operation you call xSemaphore give. So give will increase the value, take will decrease the value. And this is something you will use a lot, and one reason is that you can implement many different synchronization primitives. So you can implement mutual exclusion, which you needed to make sure you only had one task at a time in a critical region. But you can also implement many other synchronization patterns, so that we will see today. And it has a couple of constraints. For example, you can't read the value of the semaphore, which help the programmer to avoid making programming errors. And a reason why you can't read the value of a semaphore is of course that if you read it at some point in time, that value might have been changed later on, right? So you can never trust the value of the semaphore. Yeah, and if you implement synchronization using this, although it's easy to make mistakes, but it's still a much more clean and organized way than to implement some ad hoc solutions using Peterson's algorithm or similar things. And in the implementation of these semaphores, you typically use these test and set instructions that we were talking about previously to get a nice implementation. So I think the best way to look at this is to look at an example. Okay, here. So we have, in this case, two tasks, A and B, and we have a semaphore that has the initial value 0 in this case. So if in task A, here this is just a function to do something, it doesn't matter. And then here, give sem. Here we will increase the semaphore by 1. So this is an operation that will always succeed. But in task B, we will decrease the semaphore by executing the take instruction and then do some work B. So what will happen here? So how can these, so in this case, there will be some relation between in which order we execute this and this function. So let's say if we start to execute task A, what will happen? Yeah, we will do work A, of course, and then we will increase the value of the semaphore by 1. So we'll increase it from 0 to 1. And now, let's assume there is a context switch here. We'll switch over to task B. Now task B will try to decrease the semaphore. At this point, the value of the semaphore was 1, right? So it's larger than 0. So it will be, this take operation will succeed, and it will continue immediately. And then it will do work B. So we execute first work A and then work B. But let's say now the scheduler tries to first execute task B. So we starts here. It will do the take semaphore, and the value of the semaphore was initially 0. So what will happen now from the definition of the semaphore?
B goes to block state.
Yeah.
A or other tasks waiting in the ready state.
Yeah.
Can be executed.
Exactly. So since the value was 0, it will block. This task will then switch state from running to blocked, so it can't be scheduled for execution any longer. And then the scheduler has to execute some other task that is ready to execute. For example, task A. So it will start to do its work, and then when it's done, it will increase the value of the semaphore. And remember from the definition of the give of the semaphore, so now if there are tasks that are blocked on the same semaphore, one of them will be waken up, meaning it will be moved from block to ready. So let's say task B was the only one that blocked on semaphore. So that means that task B will now, when we have executed this instruction, it will be ready to execute again, and it can continue. So at some point, sometime in the future, the scheduler will now schedule it for execution, and it can continue to do its work. Right? So no matter how in which order the two tasks were scheduled, we will always have the result that do work A is done before do work B. Yeah, so I think this is just an explanation of what we just said. And yeah, you have this X semaphore take and X semaphore give. So that was is used in FreeRTOS to implement these things. Okay, so we mentioned that you can do different kind of synchronization patterns. So if you now would like to have a synchronization pattern that works in both ways, so we would like to use semaphores to make sure that do work A1 is executed before do work B2, so we have here, and we would like to make sure that do work B1 is executed before do work A2. So take a couple of minutes to think through how you could use semaphores to implement this.
Can we use more than one semaphore?
You can use more than one, yeah.
Okay. That's
So how many do you need?
2 is enough.
Yeah. And how should you Or I can give you a half a minute or something like that to think about it.
You can ask someone else. Yes.
Huh?
I've been answering so much.
Okay. Do we have some suggestions? So what should we add here? So now we would like to signal, right, that we have executed A1. So we're done with A1. So we can think in the same way as before. So we create a semaphore, we initialize it to 0, and then we increase it here. And then we create another semaphore that basically says, okay, B1 is done. And so in this case, so we increase the value here for A, and we increase the value here for B. And then we try to decrease the semaphore, but not. So here we increase for A, and now we decrease for B. Right? So remember again, so this will always succeed, but we might block here. And we will block if task B has not executed this give instruction. Right? So if that happens, it will block, and the only thing that can happen is then that if this was the only two tasks, that task B will be scheduled and it will do its work, and then it will increase the semaphore, and then we can continue to do this. Yeah. So that was one solution. Can we do it? Is this the only solution we can have? What will happen if we change the order of these two? Will it work?
Locked. It's going.
It will only be blocked if you flip it on both of the tasks.
Yeah.
Yeah?
But if you flip it on one, then you will always do it in the same order.
So what will happen here if you?
You will start doing B1, and then you will wait for B1 to be done.
Yeah.
And well, then after that it could be either A2 or B2.
So, yeah. So it will work, but there is it's not the preferred way to do it, because you might have to have multiple switches between task A and task B. So one more time than what is strictly necessary here. So although context switches are not that expensive, but still it's better if you can avoid it. So, and this was also mentioned, if we do it the take before the give, then you take here, you do the take here, and then bam, you're in a deadlock situation, because both tasks are now blocked and none of them can execute the give instruction. So nothing will happen. Okay, so during the break you can think about this mutual exclusion problem again. Can we use semaphores to implement that in this case only one of the two tasks will be executing this critical work function at a time. So how many semaphores do we need? What should be the initial value of the semaphores, and in which order do we execute the give and take instructions?
Do we have a specific order?
No?
Task
There is no order. You should just make sure that only one of them is in the critical section at a time. So the ordering we already know how to do. Okay, so we take a 15-minute break and then we continue to discuss this.